Let's talk now about change of variables in multiple integrals. And let's talk about why this is much more used in multiple integrals than it is in simple integrals. And it's because by changing the variables, we can change basically the order in which, the direction in which we are doing the integrals. So remember, when we are doing integrals, the directions x, y, and z play very important roles when you are finding the limits of integration, right? So sometimes it's easier to change our directions or change our variables so that the limits of integration become much easier, okay? And that's exactly what a change of variables achieves. So imagine that we don't change our variables. So we have two variables, x and y. Here I just renamed them u and v. So this means that we are dividing our region into lines of constant y, which are these lines here, and lines of constant x, which are these vertical lines here. Yeah, and this creates the small squares that in the limit when the square goes to 0 is what we are integrating, right? That's why the integral includes dx times dy, because that's the size of this area. Now, imagine we use two variables instead of x and y. We use these two variables u and v, which depend on x and y in this way. And actually this constitutes a tilted grid, because for example these lines here are lines of constant v. So when x minus y equals square root of 2 is a constant, we get a line like this, and when we change that constant we get different lines, yeah, while the lines of constant u are these lines here. So this means that we would be splitting the area into squares but tilted in this direction, okay? But don't worry about this because we won't do problems of weird coordinates like this. However, we will do problems where we change coordinates to polar coordinates. So this is rho and this is phi, the polar coordinates, right? So you might want to change an integral into polar coordinates, which means that now you can define the lines of constant rho. Those are circles of constant radius, yeah? And you can define lines of constant phi, which are these radial lines. So when you put together those two types of lines, you end up with a grid that looks like this, okay? So now this is your new differential of area. So now your differential of area is no longer dx times dy, but now it's something else. I will tell you later how to calculate this, but for rho and phi polar coordinates, the differential of area is equal to rho d phi. So there is this extra rho here that I will explain later, okay? But the point is that instead of having dx dy as your differential of area, we are now having d rho and d phi, which means that our limits of integration can be limits in rho and in phi, which might be useful, for example, to integrate a cylinder, okay? Because then the limits become constant. So let's theoretically talk about changing the variables, and let's remember what happens in the one-dimensional case. And the best way to do it is to refresh your mind with a simple example. So I'm going to do an example. So let's say you want to calculate the integral from 0 to 2 of x times e to the x squared with respect to x, okay? And now someone tells you this integral might be easier to solve if you do a change of variables. And the change of variables that you should do is this change, u equals x squared. So how do you change the variables to u equals x squared? You do three things. One, you change the integrand. So what do I mean by change the integrand? I mean that you rewrite this using u. So this will be x. We need to find x as a function of u. So we can actually solve for x here, and we get that x equals the square root of u. And therefore the integrand becomes square root of u times the exponential of u, because x squared is substituted by u. Okay, so that's the first thing you do. The second thing you do is you change the limits. So now the limits are x equals 0 and x equals 2. So now you need to find the corresponding limits in u. So x equals 0 corresponds to u equals 0, and x equals 2 corresponds to u equals 2 squared, u equals 4. Okay? And finally, last but not least, you change the differential. So you had dx here, but you need to change that. So dx, and to change that, you use the trick of the product rule, right? So you say that dx is equal to du over dx, sorry, the other way around, is equal to dx over du times du, right? Because the du's cancel out and you end up with dx. And dx over du is the derivative of x with respect to u. And you have the function here relating x to u. So the derivative of this is 1/2 times u to the minus 1/2 times du. Okay? Which you can rewrite as 1 over 2 square root of u du. Okay? And once you have done those three things, then you can write the integral as the integration between 0 and 4 of square root of u e to the u times, and instead of dx you write 1 divided 2 square root of u du. And this has the advantage that the square root of u's cancel, so you get 1/2 times the integral 0 to 4 of e to the u du, which is simply 1/2 e to the u evaluated between 0 and 4, which is 1/2 e to the 4 minus e to the 0, which is 1. And that solves the problem, okay? But now we are focused on arriving here or here, and the fact that we had to do these three things. So when we are changing the variables on double or triple integrals, we have to follow the exact same three steps. So first, you change the integrand, and this is as easy as in the one-dimensional case. So you just have to change from f of xy. You just need to find x as a function of u and v, and y as a function of u and v. Okay? Because remember that we are changing two variables. So in order to change two variables, we need to write two functions of x and y, which are our new variables. Yeah? We will also need the inverse expression. So if you have u as a function of x and y and v as a function of x and y, you also need x as a function of u and v and y as a function of u and v. For example, if you are using polar coordinates, this is rho and phi as a function of x and y, you also need x and y as a function of rho and phi, which, as you know, is u cosine v and u sine v. Okay? So this is similar to how when you do a change of variables, you also need to find the x as a function of u, because you need this in order to calculate the differential, because you need to do the derivative, right? So you need x as a function of u and v and y as a function of u and v. Perfect. That's step one. Step two is change the limits. And that's very easy. You have the lower limit for x, the upper limit of x, the lower limit for y, and the upper limit for y, and you need to change that into u and v. Okay? Normally, this is not simply substitution of values, but actually you need to write your new area, write your area of integration using the new limits. Okay, so for this you need to use the same technique of thinking, okay, if I'm varying the new variable u and you draw a line in the direction of increasing u, when do I enter the region of integration and when do I exit the region of integration, and that will give you the limits. And then you project into the other variable v, and you find the limits in v. Okay? And finally, you have to change the differential. So initially you had dA, which is equal to dx dy, and now you need to change that into dA, which is something times du dv. And this something is really important, okay? And it's very easy to forget it. But this something is similar to how when you wrote dx, you didn't simply change dx into du. You had to add something here, right? So this something is, for the same reason, you need something here too. So how do you calculate this? How do you calculate this? So I'm going to give you 3 ways of knowing how to write dA in the new variables. So that will be in the next video.